today's topic is viscous and thermal effects in acoustic. After a short introduction, I'll introduce the modeling assumptions we make there, go into the governing equations, and detail finally finite element formulation, and tell you what to take care about when modeling viscous and thermal effects in acoustics. First of all, we know classical acoustics, where we assume small acoustic perturbations to a base flow and a compressible but inviscid fluid undergoing adiabatic state changes. We have the governing equations, balance of mass, balance of momentum, and equation of state, and we can simplify them into the acoustic wave equations. But these assumptions, especially the inviscid fluid, might be violated in certain cases. So we need something that can take care of these cases. And we want to incorporate, in particular, viscous and thermal effects. So for modeling viscosity, we will consider a viscous fluid, in the simplest case, an isotropic Newtonian fluid. And for thermal conduction, so the thermal effects, we consider heat exchange. So the phase change, the state change of the fluid is not adiabatic anymore. So we need an equation for the conservation of energy, and that's a new conservation equation we need to solve. And especially for small devices, viscous and thermal effects cannot be neglected. I just want to motivate this now by the length scales we have in acoustic problems. So let's consider we have air as a medium with a frequency of 1 kilohertz. We have a wavelength acoustically of 34 centimeters approximately. And the length scales of the viscous boundary layer that develops in this oscillatory flow is 70 micrometers. And the thermal boundary layer, similar for air, is 64 micrometers. But now if you go into small devices, the length scale of this viscous and thermal boundary layer actually comes close to the device size, and therefore viscous and thermal effects play an important role in these problems and should be taken into account. So how can you do this in general? First, there are bulk formulations not taking into account any boundary layer effects. They model the viscous dissipation in the bulk wave propagation, and this can be done by assuming complex valued material parameters in the wave equation. You see a reference here. You can look it up at the reference page at the end. There are also acoustic boundary layer formulations that actually use impedance type boundary conditions to model viscous and thermal boundary layer effects. Also by modeling the wave equation, and as we'll see in detail later, there are the linearized conservation equation that allow a detailed descriptions of viscous and thermal effects at the expense of a larger computational effort. And here I've given a reference that is very similar in the derivation to what follows now. So let's look into the assumptions we are going to take. First of all, since we're going to small devices, it's important to know that we still deal with a continuum formulation. So we don't see the fluid as individual particles, but a continuum, and therefore we assume it can be described by macroscopic functions that are functions of space and time, like density rho is a function of the spatial coordinate x, and the time t. And in order for this continuum assumption to be valid, we must that the fluid must be sufficiently homogeneous at the considered length scale. And this is described by the Knudsen number, which is the ratio of the mean free path length of the fluid particles and a characteristic length of the problem. And if the Knudsen number is small compared to 1, continuum theory is ready. So here you see a picture of the length scale. So this is length scale, and on the vertical axis you see the density, and at a certain length scale you will see that actually there's no density variation, particle or no particle. It's simply considered as a continuum. And the second important assumption is a small acoustic perturbation. So we only consider small perturbation of a stationary base flow. So we have a base flow F0 of x that's only spatially dependent, and a small perturbation df that is dependent on space and time. And this allows us to linearize the governing equations. And as usual, we can do for time harmonic problems, make an harmonic ansatz for the perturbation quantity, and we will describe it then as the real part of a complex valued amplitude time the harmonic oscillation described as the exponential e to the power of j omega t. Just note that the base flow quantities are known, and they of course also must satisfy the governing equations, otherwise our linearization cannot be valid. So let's go into the governing equations, which are the conservation equations now. First off, we have the balance of mass, and we can obtain the total mass by integrating the density over the volume, and then in order to conserve the total mass, the substantial or material derivative of the total mass must be 0. And we can write this in the following form by using the Reynolds transport theorem. We can write this here as the partial derivative with respect to time times rho, and the convective parts of the divergence of rho times the velocity field v. And therefore we can also write the common form of the balance of mass, partial derivative of rho with respect to t plus divergence of rho v. So this is our first conservation equation. Then we have the balance of momentum as a second conservation equation. Also here I've given the form in a Eulerian control volume. We can write the conservation of momentum as rho times the time derivative of the velocity plus rho times the inner product of v with the gradient of v plus the, this is equal to the divergence of the stress tensor sigma, and g is our body force density. So the stress tensor sigma is usually written as a combination of the isotropic pressure stress tensor, so the unit tensor times p, and due to the sign convention with the minus, plus a viscous stress tensor, which we now will not neglect but take into account. The question is, how do we model viscous stresses? And for this, we will assume a Newtonian fluid, which is simply a fluid that has a linear relationship between viscous stress tensor and fluid strain rate. And for the simplest case of an isotropic Newtonian fluid, we make the usual split of the straight rate tensor into a volumetric part, EV, and the deviatoric part, E dot T, and we'll weight these two parts with the corresponding viscosity. So we have a bulk viscosity lambda for the volumetric part and a shear viscosity mu for the deviatoric part. And due to the convention, we take a factor of 2 here. So how do you compute these two parts? The volumetric part is simply the divergence of the velocity field times the identity tensor to make it a tensor in 1/3. This is the convention here. And the deviatoric strain rate tensor is the total straight rate tensor, which we can describe by the expression we already know for the deformation gradient tensor simply with the velocity instead of the displacement, and we'll subtract the volumetric part, then we arrive at only the deviatoric part of the strain rate tensor. What is often used here is the Stokes assumption. So we set the bulk viscosity to 0, so we completely neglect it. Then we arrive at the simplest possible model, which is a 1-parameter model to describe the viscous stress tensor as a function of the strain rate. And then we come to our last conservation equation, which is the conservation of energy, and we'll write this in terms of the specific entropy S in the following form. We have a few terms in this equation. On the right-hand side, we have the heat sources from viscous dissipation. So this is this term here, tau in the divergence of V, double contracted. And we have heat source density, of course, also on the right-hand side. And on the left-hand side, we have our heat fluxes. And these are described by Fourier's law, simply only considering heat exchange by thermal conduction. And K is our well-known heat conduction coefficient. And here for the fluid, since we already assumed it's isotropic in terms of the Newtonian fluid, we also make the heat conduction isotropic in the fluid. Finally, we'll need an equation of state, and we can assume we have an equation of state that relates the density to pressure and temperature, and here we can obtain a linearization by simply taking the partial derivatives. So the disturbed quantity d rho is equal to the partial derivative of rho with respect to T at constant temperature times dP plus d rho with respect to T at constant pressure times dt. And this can be written in measurable material quantities, which I'll detail just later. So we can write it in this sense. And similarly, we can do this for the specific entropy. We also write it as a function of temperature and pressure and linearize. And finally, write it as a function of material coefficients. So what are these material coefficients? Let's have a look at their definition. First, we have the isothermal compressibility, kappa T, which is defined as -1 over the volume and times the partial derivative of the volume with respect to the pressure at constant temperature. You can rewrite this in terms of the density. You can also define the isentropic compressibility. This is actually the compressibility we already know from classical acoustics, is denoted Ks. S stands for constant entropy, so isentropic, and it can actually be related to the isothermal compressibility via the specific heat ratio gamma. And then it can be related to the isentropic speed of sound, C and the density. So you see actually it's the inverse of the isentropic bulk modulus. And the last material coefficient we need is the isobaric thermal expansion coefficient, denoted by alpha, which is defined as 1 over the volume and the partial derivative of volume with respect to temperature at constant pressure. And again, you can write this in terms of the density too. Here on the right-hand side, I've given for your reference a few relations between the material parameters that are not straightforward at the first glance, but you can use them to compute one from the other. So they're given here for your reference. Okay, let's look at this in for an ideal gas as an example. We have the ideal gas law. Rho is P over RT, where R is the specific ideal gas constant. You can compute it as Cp minus Cv, so the difference in specific heat at constant pressure minus volume. And then you can do the partial derivatives, and you end up with these relations. And similarly, you can do this for the definitions of alpha p, kappa t, and kappa s. And when you do all these derivatives, you see that for ideal gas, alpha p is 1 over t, kappa t is 1 over p, and kappa s. From this relation, you can actually derive the speed of sound for an ideal gas, which is simply the square root of gamma times P over rho. Okay, so now I'll quickly describe what is necessary for the linearization procedure to linearize the conservation equations for mass, momentum, and energy. The first step is to use the perturbation ansatz for all the quantities. And then we'll restrict ourselves for the case of zero background velocity simply to make the expression shorter. Assume that the conservation equations are satisfied for the base flow, and introduce the linearized constitutive relations. And you can do this to replace d rho and ds by dp and dt. And finally, of course, in the linearization, we will drop all terms of higher order in the perturbed quantities, and you will see that this will yield 3 partial differential equations for the perturbed quantities, pressure, velocity, and temperature. And to make the notation a bit simpler now, since we're only interested in the perturbed quantities, we'll in the following denote them simply with P, V, and T for the sense of brevity, but be aware of that from now on we only speak about perturbed quantities. So how do these equations look like? The linearized compressible flow equations, we can solve these 3: balance of mass, balance of momentum, and balance of heat or energy for the pressure, velocity, and temperature field. In fact, there is a simplification if you consider if you want to disregard thermal conduction. You set the thermal conductivity to 0, and you actually see that equation 22 becomes a relation between temperature and pressure. Of course, this also only makes sense if you have no heat sources. And in this case, we can actually we consider the phenomenon as adiabatic, so we have no heat exchange between the particles anymore, which makes the energy relation not a partial differential equation anymore, so it's obsolete, and we can simply describe the temperature as a function of the pressure only, and insert this into the balance of momentum, and this yields the linearized Navier-Stokes equations that are given here. So we only have a balance of momentum, equation 25, and the balance of mass, equation 24, with the solution quantities of pressure and velocity field. Okay, so in order to solve a boundary value problem, of course, we also need boundary condition. And here a few useful boundary conditions are given. First, we have the velocity, which is usually known at the boundary. Usually it's set to 0, for example, for a fixed wall. but in most generally it's known. Temperature, similar a Dirichlet boundary condition. On the temperature field, we have the mechanical traction in normal direction, so sigma in n, which is a known traction vector sigma n at the boundary. We can employ impedance boundary condition, where we actually relate the traction to the normal velocity times so-called impedance z. And we have a heat flux boundary, which is simply Dirichlet boundary condition inhomogeneous for the heat conduction PDE. Note on the impedance boundary condition, you can actually make it become an absorbing boundary condition if Z is chosen correctly, and it must be chosen as the impedance of a traveling wave traveling plane wave, I have to say, in normal direction. Okay, so let's go into the finite element formulation, where the weak form is obtained from the strong form in the standard way. So the first step is multiply our governing equation, balance of mass, momentum, and energy, with the test functions p prime, v prime, and t prime, and integrate over the complete domain. And then we integrate by parts using the divergence theorem and incorporate the boundary conditions. And this gives us the following weak form, where we have the balance of mass equation here with, you see here, a term with time derivatives for pressure and pressure, so bilinear form with the pressures, mixed bilinear forms with pressure and temperature, again with the time derivative, and mixed bilinear forms between pressure and velocity. In the balance of mass, we have not done any integration by parts. We have the momentum equation, which is a bit longer, but very similar to the equation we have in classical mechanics, since we put in the expression for the stress tensor already. In effect, we have here now a bilinear form between velocity and velocity in the first line. These are the parts that come from the viscous stress tensor. And we have a mixed bilinear form, which comes from the pressure part of the stress tensor here in the second line, with divergence of v prime and the pressure p. And we have the boundary terms, first from the impedance boundary condition that gives us a bilinear form in terms of the velocities, and on the right-hand side, the forcing from a known surface traction sigma n, and the volume forces due to known volume force densities G. And again, for the heat equation, this is actually very similar to the classical heat equation. We have a mass term here, bilinear forms between the temperatures. We have a classical stiffness term with the gradient of the temperatures, and we have a mixed term, bilinear form between temperature and pressure, here again with the time derivative. And on the right hand side, we have the classical boundary terms of the heat flux over the boundary, or a volume heat source density. Okay, and so now we have the weak form. We can actually apply the classical Galerkin procedure, introduce a suitable, as we split the domain into finite elements, we introduce suitable ansatz functions for the unknowns, and apply the Galerkin procedure, and we'll obtain a semi-discrete system of the form given here. So we have one could call it the damping matrix in front of because it's in front of the unknowns with the first time derivative, and a stiffness type matrix in front of the unknown vector itself, and on the right hand side we have forcing vectors. large parts of the system matrices are actually 0, and our degree of freedom vector x now contains all the unknowns for pressure, velocity, and temperature. What is important to mention here is that one needs to use elements with ansatz functions of order k for the pressure and one order higher, so k plus 1 for velocity and temperature fields. So these elements are called so-called Taylor-Hood elements. And this is necessary to satisfy the inf sub or LBB condition. Okay. So finally, I'll want to detail a little bit the modeling approach that we use for thermoviscous problems in acoustics. So first we have a few analysis types that are meaningful. The first one is the harmonic simulation. So we solve for the steady state for harmonic excitations, and we need to solve one linear system per frequency step. The second analysis type that makes sense is an eigenvalue analysis that yields us natural frequencies, damping factors, and corresponding oscillation modes. And for this, we need to solve a generalized eigenvalue problem with unsymmetric matrices in the current form. And finally, there's the transient solution, where we have given initial conditions for all the field quantities, and we have loading histories, and we can obtain our transient solution by integrating the ordinary differential equation system by numerically in time. So when you model, we have a typical problem description. First, we have typically a flexible structure that's often of interest, and it's surrounded by viscous compressible fluid. We have very small gaps that make it necessary to incorporate viscous effects. And typically, we also want to know the acoustic far field. So to save computational resources, we should switch to more efficient wave equation type formulation as soon as possible. The coupling between solid mechanics and acoustics is done efficiently with non-conforming grids. And this is actually the topic of the next lecture. So let's look into the meshing requirement for the linearized flow equations. First, as in acoustics, always we have to resolve the acoustic wavelength. So the rule of thumb, 20 degrees of freedom per wavelength is a good starting point here. But we also have to know that viscous and thermal boundary layers will develop at the boundaries. And these boundary layers we also need to resolve, which is typically requires a much finer mesh than for the acoustic wavelength. And a good rule of thumb for the boundary layers is actually to use 4 to 10 degrees of freedom in the thickness direction of the boundary layer. The tangential resolution of the boundary layer might be important too, but this seems to be problem dependent. What you in general should avoid is too distorted elements. And what you always should consider is in the linearized flow equations, each node has pressure, velocity, and temperature degrees of freedom. So 5 degrees of freedom in 3D. So coarsen the mesh away from the boundaries where you only need to resolve the acoustic wavelength in order to save computational resources. Just to give you an idea, I want to show the viscous boundary layer so you can estimate what mesh resolution you should consider here. So we have an infinite half space, so the whole epsilon greater 0 space, and the border at the bottom, the plane y0 is oscillating in x direction. So then the flow field will depend only on the y coordinate, and we can make the ansatz where we have only an X component in the flow field, a Y and Z component are 0, and the pressure variation is also 0. And this actually trivially satisfies the balance of mass and the balance of momentum in Y and Z direction. And only one equation is actually remaining, and this is given here. And you can see actually here now the boundary conditions. We have a harmonic oscillation at the boundary, and at the far field, of course, we have to, we expect 0 velocity component. And then we can actually give the analytical solution here, where we see we have exponentially decaying amplitude of the velocity, and the decay factor is actually given by the viscous boundary layer thickness delta mu given here. And you see it actually depends on the frequency of interest and on the viscosity and density, so the material parameters of your medium. So this is the boundary layer thickness you should take into account when you design your mesh. Of course, this is frequency dependent. As boundary conditions and loads are concerned, in physics, usually we have a solid wall as a boundary of our domain. There we want to prescribe a non-slip conditions of 0 velocity. The wall is immovable, and typically we prescribe 0 temperature there, since we consider only the perturbations in the temperature in our formulation, and the thermal conductivity of the solid is usually much larger than of the fluid, so it's almost staying at constant temperature. So 0 temperature variation here is a good assumption. In case of symmetries in the domain which we want to exploit, of course we need to have 0 normal velocity components and 0 tractions and 0 heat flux across symmetric boundaries. And in terms of the excitation, it's most useful to prescribe traction or velocity directly. The pressure is a sort of inner variable in this formulation, so it's not as suitable for an inhomogeneous Dirichlet boundary condition, since there's no physical meaning to prescribing the pressure directly. The physics is the traction at the boundary. That is also including the viscous parts of the stress tensor. The natural boundary conditions, since that's what happens in the finite element formulation if you don't specify something explicitly, is 0 normal heat flux and 0 traction. As for the heat and balance of momentum equation, usually it is. And the solution variables, always consider this, are only perturbed quantities. So finally, this implementation I presented here is implemented in openCFS, and it is called LinFlow PDE. So in the input scheme, it's the tag is fluid mesh lin, and be aware that this formulation is implemented in several forms. One is for the compressible linearized Navier-Stokes equations. There's also an incompressible variant in the same PDE. And if you want to take the heat conduction into account, this is implemented as a direct volume coupling to the heat partial differential equation. So the heat PDE that you already know. Together, the implementation is for the full linearized compressible flow equations. So here I've given a few references. You can look them up if you're interested.